Yeah, see here, I'm sharing my screen. Today we are going to explain, I'm going to explain this SR flip-flop, operation of SR flip-flop and SR flip-flop and D flip-flop. Okay, not D latch. This is SR flip-flop and D flip-flop and RTL design, RTL code as well as test bench. Okay, as well as test bench. Okay, D flip-flop. Okay, D flip-flop. 1 second. Yeah, 1 second. Okay, so I'm sharing my screen. 1 second. Yes. So I will explain you the operation of SR flip-flop and D flip-flop, and we'll go with this RTL code and test bench by using. 1 second, I got a message. Okay. Uh, 1 second. If you have any query, any questions or queries, okay, just after completing this session, I will ask. So I'll ask you. You can ask me, and I will clear your doubts. Okay, after completing the session only. Okay. Yes. Uh, so we'll see this SR. So first we'll see the SR flip-flop. Okay, basically in the last class I told you the SR latch. No, so SR latch by using NAND gate. What you got? So that means you got the reverse like. So this is 1 second. Yes, my screen is visible. No, anyone give response? Yes or no? My screen is visible. No. Yeah, anyone? Yes.
Yes.
Okay. Okay. Thank you. Okay. See here. Uh, so basically, in the last class, we seen the SR latch by using NOR gate and the NAND gate. I told you to do. Okay, this is the SR latch by using NAND gate. So when you analyze this, okay, when you analyze this, so what you are getting means. So here, if you see this one, so when you analyze this, this is S and R. Okay, S and R, and the present state is Qn, and next this one is Qn bar, and this is the present state, and next state is what qn plus 1 and qn plus 1 bar. Okay, so what you will get, the truth table means s r and qn plus 1, qn plus 1 and state, qn plus 1 and state. Okay, so 0 0 0 1 1 0 1 1. Okay, so what state you will get? This is just opposite of SR gate you will get. Okay, so that means this is the invalid state. Okay, this is invalid state, and this is set state. Okay, set state, and this is reset state, and this is memory state. Okay, this is the memory state. You will get this truth table. Okay, so here what I am doing. So SR flip-flop, SR flip-flop, I'm designing using NAND gate. Okay, so here in the latches, what happens means, so the outputs are, you are getting the outputs in uncontrolled way. Okay, so you need to control these outputs. Okay, so in order to control these outputs, what you need to do means you need to connect a gated clock. Okay, you need to connect a gated clock. That is, we can use this clock as passage or net gauge. Okay, so here I am using passage of clock. So here what happens? Suppose here I'm connecting one more NAND gate, and here also one more NAND gate I'm connecting. Okay, one more NAND gate I'm connecting, and so here I'm giving these inputs are what, S R. Okay, this is SR latch. Okay, this is SR latch. Okay, so this is SR flip flop. Okay, SR flip flop means you have clock. Okay, clock is a control signal. So clock, this is clock. This is passage of clock. Okay, and reset will be also there. Basically, we are using asynchronous reset. Okay, asynchronous reset we are using. Okay, reset is also there. I explain with reset, it will be complicated, but in programming, I will tell you with reset also. Okay. Asynchronous active low reset we are using. Okay. So uh, this is an AND gate. Okay. And output will be feedback like this. And here also output will be feedback like this. Okay. And what is the present state? Present state is Qn. Present state is Qn. And here this is Qn bar. And next state is what? Qn plus 1. And complement, this is what? Qn plus 1 bar. Okay. Qn plus 1 bar. So here first I am drawing this characteristic table. So characteristic table, what is characteristic table? S, R, Qn, okay, and next Qn plus 1, Qn plus 1, and here I can write the state, okay. So here if you, so three inputs are there, how many possible combinations? Three possible combinations, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and next 1, 0, 0, 1, 0, 1, and next 1, 1, 0, 1, 1, 1. Okay, 1, 1, 1. Okay, so here first case we'll see. Okay, so when s equal to so s equal to 0, s equal to 0 and r equal to 0, clock I am taking as 1 only. Okay, so clock I am taking as 1. So here you see the NAND gate truth table. What is the truth table for NAND gate? A, B, and output is Y. Just complement of AND gate is nothing but NAND gate 0, 0, 0, 1, 1, 0, 1, 1. Okay, if any one of the input is low, the output is high, and here the output is low. Okay, both inputs are high, the output is low. So that means from this I can say 0 NAND 1, 0 NAND 1 equal to what? Here you are getting 1, and 0 NAND 1, 0 NAND 1, here you are getting what? So let us take this is what? Q equal to first case 0, and this is nothing but 1. Okay, so this is 1. Okay, so that means 0 and 1. So here also 1 and 1. So here what you are getting 1. Okay. So if you see the SR latch, if it is 1 1, what is the state? The next state is memory state. Whatever the output. Okay. So that means memory state. So that means if you are taking Qn is equal to 0, Qn plus 1 also you are getting 0. Okay. If you are taking Qn equal to 1, you are getting the Qn plus 1 also 1. Okay. That analysis we already did, but I am using this truth table in the flip-flop. Okay. So here 1, and uh, this is 0, and here you are getting 0. Okay, here you are getting 1. Okay, this is 1, this is 1. So then from this I can say that when s equal to 0, r equal to 0, it will be which state? Means memory state. That means 0 and 1. Okay, and this is which state? Memory state. Okay, memory state. Okay, so this is the first case is completed, and second case I will check. What is the second case? Second case is s equal to 0 and r equal to what? 1. Okay, so clock is always 1 only. Okay, clock is always passage of clock is always 1 only. So what you are getting? So 0 and 1. So 0 and 1 means second case I am checking. 0 and 1 means what? Here this is 1. Okay, 1 and 1 means what? 0. Okay, 1 and 1 is 0. So 1 and 1, 1, 0. So 1, 0 means in SR latch, 1, 0 means what? Reset state. Okay, so reset state means what? Here you are getting what? Reset state. That is nothing but 0, 0. So this is reset state. Reset state. Okay, and next case I will check. So what is the next case? Say, third case is S is 1 and R is 0. Okay, S is 1 and R is 0. Okay, so 1 1, 1 1 means what? You are getting 0 here, and 1 1 0 here you are getting 1. Okay, here you are getting 1. So that means 0 1 means what? 0 1, this case 0 1 means what? Set state. Okay, 0 1 means what? Set state. So this is set state. This is set state. Okay, and next case. So what is the next case? S equal to 1 and R equal to 1. S equal to 1, R equal to 1 means 1 1 means what? 1 1 means here you are getting 0. Okay, here you are getting 0, and here also you are getting 0. Okay, so 0 0 0 0 means what? Invalid state. 0 0 means invalid state. So this is invalid state. Okay, this is invalid state. Okay, so that means from this characteristic table I can draw the truth table. I can draw the truth table. How you can draw the truth table? Here I'm seeing this the characteristic table and I'm drawing the truth table. Okay. So here, here I'm doing this truth table. It means yes, yes, R, Qn plus 1 and state. Qn plus 1 and state. Okay. So just two inputs only. What are the possible combinations? So here 0, 0, 0, 1, 1, 0 and 1, 1. Okay. 1, 0 and 1, 1. Okay. So here if you see. So when it is 0, 0, you see this table. You see this table. Okay. So if you see this table and just draw the truth table. Okay. So what is the truth table? So 0, 0 means what? QN, memory state, memory state. Okay. And next 0, 1. 0, 1 means what? Reset state, reset state. Okay. And 1, 0 means set state, set state. 1, 1 means invalid state. Okay. 1, 1 means what? Invalid state. Okay. Invalid state. Okay. So this is the characteristic table and this is truth table. Okay, this is truth table. Okay, and after
How
that,
it is? Can you please repeat?
what you are asking?
How it is like how you have defined this state as memory different state and valid. Can you please
Here from
repeat
the
it?
characteristic table, I got no. Here you see 0, 0 means whatever this present state, this is present state is, this is next state. If it is 0, you are getting 0. If you are 1, it is 1. So that is the memory state. If it is 0, 1, either Qn is 0 or 1, you are getting reset state. And 1, 0, what is this set state? This is nothing but next state. Next state I am writing in terms of this. Okay. 1, 1 means what? Invalid state. 1, 1 means invalid state. Is it fine?
Yes.
Okay. Next you see. So from the characteristic table, I want to draw the excitation table. Okay. So how to draw the excitation table? Here I am drawing the excitation table. One second. So from the characteristic table, you will get the excitation table. So this is a excitation table. Excitation table is nothing but what? With the present state and next state, I need to get the inputs. This we are going to use in the counters, synchronous counters. Okay, these excitation tables. So what are the possible combinations? 0, 0, 0, 1, 1, 0, 1, 1. Okay, so that means if it is present state is Qn, Qn plus 1. If it is 0, 0. Okay, what are S and R values? Okay, so you need to see here. See this one. 0, 0 means what? This one. Qn and Qn plus 1 is 0, 0 and this one. Okay, what are S and R values? Tell me the S and R values 0, 0, 0, 0 and 0, 1. 0, 1. If you combine what you are getting, 0 don't care. This is 0 don't care. Okay, and next when it is 0, 1, when it is 0, 1, what is the case? 0, 1. This is only the case, second case. Okay, so when it is 0, 1, what you are getting? 1, 0. 1, 0. Okay, this is 1, 0. Okay, and next if it is 1, 0, if it is 1, 0, so what is the case? I need to see the present state and next state. This is the third case. What I am getting? Third case is 0, 1. Okay, this is 0, 1, 0, 1. Okay, and next if it is Qn and Qn plus 1, yes, R. Okay, and here if you see, this is 1, 1. 1, 1 means what? 1, 1 means this is fourth case. 1, 1, where you will get 1, 1. This is the fourth case. Okay. If it is 1, 1, what are the outputs? 0, 0 and 1, 0. This is 0, 1 I can consider as don't care 0, don't care 0. Did you understood how I'm drawing the excitation table? From the characteristic table, you'll get the excitation table. Is it fine? This is excitation table. Okay. And from the excitation table, you can draw the state diagram. Okay, you can draw the state diagram. So how I can draw the state diagram? One second. So from here, I can draw the state diagram. Okay. So if you see, uh, so how many states are there? Like two states are there. So let us take this is 0 and this is 1. Okay, this is 1. Okay, so if present state is 0, okay, present state is 0, what is the next state? It will be in the same state. It will be in the same state. What are the inputs? 0 and don't care. Okay, this is over. If present state is 0, what is the next state? It is going from 0 to 1. It is going from 0 to 1. What are the inputs? 1, 0. Okay, and next you are at 1. You are at 1. If present state is 0, present state is 1, what is the next state? It is coming to 0. Next state is 0. Okay, what are the inputs? 0, 1. Okay, and you are at 1. If present state is 1, it will be in the same state. It will be in the same state. What are the inputs? Don't care. 0. So this is the state diagram. State diagram. Okay, and what is characteristic equation? Characteristic equation will get the from the characteristic table only. So here Qn plus 1 equal to, you need to write the minterms. What are the minterms? Summation of m of 1. Wherever the ones are there, you need to write 1, 4, 5. And how many don't cares are there? 2 don't cares. Summation of don't cares of 6 and 7. 6 and 7. So you need to draw the K map. Okay, you need to draw the K map and you need to get the logic expression. Okay, so here, so this one, so here this is S, R, Q, N. These are the inputs 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 2, 3, next 4, 5, 6, 7. Okay, write the minterms 1, 4, 5, 6, 7. Depending on the possibility, I can consider don't care as what 1. Okay, so that I will get a quad. I will get a quad, and this is pair. Okay, so pair will eliminate how many variables? One variable, no? So I can write Qn plus 1 equal to what? This is S. S plus this is what? R bar Qn. S plus R bar Qn. R bar Qn. Okay, this is my characteristic equation. Characteristic equation. Okay. So from the flip-flop, you have characteristic table, truth table, excitation table, state diagram, and characteristic equation. Is it fine? Any doubts in this? If you don't have any doubts, I will move forward. Anyone? Shall I move forward? Hello. I'm
Yes,
audible?
sir.
Yeah. I'm audible? Okay.
Yes.
Okay. Yeah. Next you see, next D flip-flop. Okay. So D flip-flop is nothing but when this S and R are tied together, you'll get D flip-flop. Okay. So SR flip-flop I drawn, no. So SR flip-flop I drawn. So that means with an AND gate I drawn the SR flip-flop. So here data delay flip-flop, or we can call as a sequential buffer also. So here this will be feedback. Okay, this is an AND latch, and here this is one more NAND gate you are connecting, and this is connected to clock. Okay, this is connected to clock, and this is yes, and this is R, S and R, and these both are tied together. Okay, these both are tied together. So that means in which cases we are using S and R. One second. S and latch, no? Okay. Tied together. Set latch. Okay, these are not tied together. These are connected with an inverter. These are connected with an inverter. Okay. So there JK flip-flop or J and K are connected together. We are getting T flip-flop. Okay. So this is nothing but a data flip-flop or D flip-flop. D flip-flop. Okay. So D flip-flop. So that means what cases I am using? This case, these two cases I am using. So when S equal to 0, R equal to 1. When S equal to 1, R equal to 0, I am using. Okay. So from this, you can see, so operation is same. Suppose suppose S equal to 0 means what? 0 means anyway clock is 1. Okay, clock is 1. Okay, and this is what? This is 1. Okay, 0 and 1. 0 and 1 means what? So from the NAND gate, 0 and 1 equal to what? So this is 1 and this is 0. Okay. When it is 1 and 0, what is the state? So Qn and this is the next state Qn plus 1, Qn plus 1 bar. Okay. So what is the state? So 1 0 means what? Set state. Okay. 1 0 means 1 0 means here you are getting reset state. Okay. NAND gate, NAND latch 1 0 reset state. Okay. So NAND latch 1 0 reset state. Okay. So this is the two possibilities if you take, you are getting reset state only. Okay. So two possibilities you take, you will get the reset state only. And S equal to 1 and R equal to 0 if you take. So what happens? 0 1 means what? Here you are getting 0 1 1. 1 1 means what? This is 1 1 clock. 1 1 means 0 and 1 0 means 1. Okay. So when in this case, whatever may be 0 or 1, 1, 1 and 0, it will be what? Set state. It will be which state? Set state. Okay. This is set state and this is reset state. Okay. So that means whatever the input is there, you are getting at the next state. Okay. That is nothing but D flip-flop. So I can draw the characteristic table. So how we can draw the characteristic table? D, Qn and next Qn plus 1. Okay. How many possible combinations? 0 0 0 1 1 0 1 1. Okay. So if you combine, if D is 0, whatever may be this Qn and 0 or 1, you are getting 0 0 only. Okay. If D is 1 1, whatever may be the Qn 0 or 1, you are getting 1 1 only. Okay. Sequential buffer, whatever the input is there, you are getting at the next state. Okay. And this is characteristic table and next truth table. So what is truth table? D Qn plus 1 state. Okay, D Qn plus 1 state. Okay, so this is 0 1. Okay, so 0 1 and so what is Qn plus 1? Qn plus 1 is 0 only. Okay, this is a reset state. 1 1 means what? Set state. 1 means set state. Okay, and excitation table. So excitation table means what? Here with present state, next state, and D input. D input. Okay. So 0 0 0 1 1 0 1 1. Okay. So here if you see 0 0 0 0 means what? 0. Okay. Present state and next state I need to see. Okay. 0 1 0 1 means what? 1. Okay. 1 0 means 0. 1 1 means 1. Okay. So the beauty of this D flip-flop means if you know the next state, directly you can draw the next state. So next state values you are getting at the output. Okay. Next state values you are getting at the output. Okay. So that is the beauty of this D flip-flop. So if you know this next state values, directly you write. Don't you no need to remember the excitation values. Okay. So whatever these values are there, you can write same thing. Okay. No need to remember the excitation table. And characteristic equation. One second. Characteristic equation. So from the characteristic table, you'll get the characteristic equation. Okay. So how you'll get the characteristic equation? So characteristic equation means you need to draw the K map. Okay. So here, what are the inputs? D, Qn, 0, 1, 0, 1. Okay, 0, 1, 2, 3. Okay, and so here 2, 3 are 1, 1, 1, 1. This is a pair. Okay, so Qn plus 1 equal to what? D. Qn plus 1 equal to D. And next state diagram. How to draw the state diagram? From the excitation table, you can draw the state diagram. Okay. So this is state diagram. State diagram. So present state 0 and this is one more state 1. Okay. You are at 0. Okay. What is the next state? It will be in the same state. Okay. What is the input? 0. Okay. You are at 0. What is the next state? It is going to 1. What is the input? 1. Okay. And you are at 1. What is the next state? 0. 0. Okay. This is what? 0. Okay. Input is 0. And you are at 1. So what is the state? It will be in the same state. Input is 1. Okay. So this is the state diagram. So I drawn the for D flip-flop, characteristic table, truth table, excitation table, characteristic equation, and state diagram. Okay. For all those things I wrote. Is there any doubt or any query? If you don't have any doubt, I will go for programming. Hello. Give response, any doubt or any queries so that I will move forward. Okay. Okay. Thank you. Okay. I'll go for the programming. Okay. So I wrote the programming. Yeah. See here. 1 second. I will open this. Xilinx Vivado. Please wait. It is opening. Xilinx Vivado. This software will take 35 GB of memory. Okay. If you want to download, there is some steps are there. From the AMD website, you need to download. I'm using 20.1 version. So this one, yeah. See here. First, I wrote the program for what SR flip-flop. Okay, SR flip-flop with asynchronous active low reset. Asynchronous active low reset. Okay, so I will explain the program. See here. First, Verilog code will start with what module and module name. What is the module name? Identifier. That is identifier SR underscore flip flop asynchronous. And whatever the inputs are there that I need to initialize with wire data type. Okay. I'm using behavioral modeling. Okay. So inputs I need to initialize with wire data type. Input wire S, input wire R, input wire clock. Okay. Input wire reset underscore N. Okay. This is the fixed standard variable representation. If it is active low asynchronous reset, I need to initialize with reset underscore n. Okay, and output is what? Output is reg q. Okay, output, if it is a behavioral modeling, output I need to initialize with reg data type. Okay, after that, this one I need to initialize as y data type. Why? Because I am using a continuous assignment statement. Assign. Okay, assign q bar equal to what? Not of q. When you are using the continuous assignment, that should be y data type. Okay, that we need to remember. Okay, so that's why q bar equal to what? Not of q. This is a logical operator. Always at the rate passage of clock and negate of reset. Okay, so that means this is asynchronous active low reset. Okay, asynchronous active low reset means what? Reset removal is synchronous with the clock, but reset applied is synchronous with the clock, whereas reset removal is asynchronous with the clock. Okay, irrespective of clock, it is independent of clock. Okay, so why we are using means sometimes what happens, suppose if you are using synchronous reset, sometimes what happens, so that is reset removal and reset applied and reset removal. Reset removal and reset applied is synchronous with the clock means sometimes my clock will not work. Okay, so most of the designs will use this active low asynchronous reset only. Okay, so I'm using a condition if not of reset. So I'm clearing the output q equal to 0, else begin. So I'm using a case statement. Okay. So case statement. What is the case statement? So I'm using the concatenation operator s comma r. So that is 0 0 means what? No change. 0 1 means 0. 1 0 means set state. And 1 1 means invalid state. Same whatever the truth table I explained, I'm writing in the case statement. End case. Okay. And end. Okay, begin end and end. Okay, this one where you else begin is there, no? This begin you need to end. Okay, always at the power this begin you need to end and end module. Okay, so this is the program. Okay, after that I need to write the test bench, no? Here you write the test bench. See here. This one I wrote the test bench. Okay, so in the test bench there are five steps are there. This is the module test bench name, and whatever the input variables are there I need to initialize with reg data type, and output variables are there I need to initialize with y data type, and I'm initializing one more integer I. Why? Because here I'm using for loop. Okay, so that I am initialized as a integer data type. Okay, integer data type, and this is nothing but instantiation. Okay, this is nothing but connection by name. So that is nothing but design name. Okay, I'm instantiating that design. Okay, so what is my design name? SR underscore flip flop underscore asynchronous unit under test. Unit under test. Whatever the variables are there, those outside the variables, those are nothing but design inputs, design inputs, and whatever the variables inside the bracket, those are test bench inputs. Okay, so this is nothing but instantiation. Okay, So I told you, no, there are two types of instantiation, connection by position with order list or connection by name. Okay. So basically in industry, we'll use the connection by name only. At this nomenclature we need to use. Okay. So this vertically I need to give. Okay. Why? Because some design have some 100 inputs or 150 inputs. Okay. So we need to identify each and every input. Suppose one input is missing means you will get a like bug in your design. Okay. So this is SR flip-flop. This is instantiation. Okay. And I need to generate the clock initial begin. So clock equal to 0. I'm using a forever. Okay. And I'm using a delay function. That means hash 5 is nothing but for 5 time minutes. I'm introducing a delay. Clock equal to not of clock. So this is what is the clock period? So half clock is 5 time units. So what is the clock period? Total clock period is 10 nanoseconds. Okay. So I need to generate the clock for forever. Okay. Clock will be forever, no? So or always also we can use. Okay. Here I can use always also. Okay. Nothing will be done or nothing will happen. Always also I can use or I can use forever also. Okay. So and end. Okay. So this is clock generation. After that, I need to give the stimulus. So initial begin. So dollar display. I want to display SRQ, this truth table. And if there any change in the dollar monitor is also system task. Okay. System task means if there any change in the input, it will execute the outputs. Okay. And applying first, I'm applying the asynchronous reset. Okay. Whatever the reg variables are there, I need to clear for seven time units. And so reset I'm making as 0, no? So reset I'm making as 0 for 7 time units, and after that I'm releasing the reset. I'm making reset equal to 1. So when reset equal to 1, it will go from where to where? This is reset mode. Okay, this is reset mode. After 7 time units, it will go into the functional mode. Okay, it will go into the functional mode. Try for all input combinations. Okay, what are the input combinations? 0 0 0 1 1 0 1 1. Okay, so for this I'm writing the for loop. For I equal to 0, I less than 4, I equal to I plus 1. Begin. Okay, I'm using concatenation operator s comma r. I of 1 is to 0. So I of 1 is to 0 means 2 bits, no? 0 0 0 1 1 0 1 1. That's why I of 1 is to 0. Okay, I'm using this array. Okay, and I'm using this is I'm executing for every input. I'm executing for 10 time minutes. So delay is the 10 time minutes. Okay, end. Okay, and after that, after completing this for loop, after 10 time minutes, I need to end the simulation. That is dollar finish. Okay, and where I wrote initial begin is there, no? So this begin I need to end and end module. Okay, so this is the test bench. Okay, so this is the test bench. Next, what I need to do, I need to I need to see the waveform. Okay, so this is anyway top module. 1 second. I want to see the simulation. SR flip-flop, right click in the simulation, and I need to make a stop module. I need to make a stop module. Okay, here three dots are there means it will be top module. Okay, and what I need to do, I need to see the circuit. Okay, elaborate. So go to this and elaborate the design. Okay, save this file. I want to see how this. So if I'm writing the program, compiler will generate the hardware. Okay, so I want to see the netlist is generating. Just wait, it is generating the netlist. Yeah, see here. This is the hardware generated by my uh, my tool. Okay, my EDA tool. Okay, okay. So like this. Okay. Suppose if I want to see the simulation, so run behavioral simulation. Run behavioral simulation. So asynchronous reset means directly I need to connect this bubble like this. That is asynchronous reset. So you can see the truth table in the TCL console also. Okay. 1 second where I got. Okay, we'll see the waveform. Okay, waveform. See here. So this is the waveform. Fit to page. 1 second. Okay, what it is executing? D flip-flop it is executing. 1 second. I'll close this. I want SR flip-flop, no? I'll close this. Syntax error. Where I'm getting. So SR flip-flop set as stop. Set as stop. And run simulation. Run behavioral simulation. Yeah. Yeah. Where I got this one. 1 second. I'm getting the error. Okay. I need to see the errors. The TCL console. 1 second. Mm, Close this. Still syntax error. Near end modulo. TBSR asynchronous. 1 second. TBSR asynchronous. Mm, TB. Okay. SR flip-flop. TBSR asynchronous. So I'll see. Okay. End module. End module. So this end I need to give. I think it will go. Shall begin end. Shall begin end. Okay. So I'll save this. Yeah, it's gone. Okay. Yeah, see here. So SR flip-flop I need to see, no? So set as stop, set as stop. Yeah. So run the simulation, run the behavioral simulation. Here, see here. In the TCL console also, I got the SR flip-flop outputs. Okay. S equal to 0, R equal to 0, Q equal to what? 0. Okay. S equal to 0, S equal to 0, R equal to 1, Q equal to 0. S equal to 1, R equal to 0. S equal to 1, R equal to 0, you are getting Q equal to 1 here. Okay. Like that, you are getting this. So if you see the waveform, just you see this fit to page. Here, what happens means, so just bring this line. So this is a asynchronous active low reset, no? So that means during this reset, okay, during this reset, what happens? So when reset equal to 0, the what happens? The output will be 0 only. Okay, the output will be 0 only. Okay. So when reset becomes 1, then it will go from what till here it will be in which mode? Reset mode only. Why? Because reset equal to 0. Okay, when it is going from here to here, it is going from where to where? Reset mode to functional mode. Okay, so through it is going from reset mode to functional mode. So when the output will change means during next passage of clock the output will change. Okay, so immediately it will not output will not change. Okay, so when you will get output means during this passage you will get the output. Okay, so that means reset removal is what? Synchronous with the clock. Okay, when it is going from reset mode to functional mode, in the functional mode it is synchronous with the clock. Okay, so here in this during this one, whatever the input is there, you are getting the output. Okay, so see here in this S equal to 0, R equal to 0. This is nothing but previous state. What is the previous state? 0 is there, no? So previous state is 0 means you are getting same state. Okay. And next, during this next clock edge, S equal to 0, R equal to 1. Reset state. Reset state. Okay. Reset state only. And during this passage of clock, S equal to 1, R equal to 0. Okay. This is nothing but what? Set state. Okay, this is nothing but set state. Okay, and during this passage of clock, S equal to 1, R equal to 1, invalid state. This truth table is verified or not? When 0 0 memory state, 0 1 reset state, 1 0 set state, 1 1 memory state. Okay, this is SR flip flop. Okay, hope you understood. And next we'll go with D flip flop. So I'm doing this D flip flop, right click, set as stop, and this D flip flop also right click, set as stop. Okay, so if you see the D flip flop, yeah, see here. So this is the diagram for the D flip flop. Okay, this is the Verilog code for D flip flop. One second, one second. Yes, sir. D asynchronous. Yes, sir. Yes, sir. Asynchronous. This is D. Okay, see here. So module D flip-flop. This is identifier. This is a module name. Input wide D. How many inputs are there? Only one input is there. Input wire clock. Whatever the inputs are there, that I need to initialize with the wire data type. Okay. So input wire set n, and I'm using what asynchronous active low reset. Okay. This is the predefined variable for representing asynchronous active low reset. Okay. Output reg q. Okay, always at the rate passage of clock or negate of reset if not of reset. Okay, so that means what, so if reset equal to 0, q becomes what, you need to clear the output, no? So that means it is nothing but if it is there in reset mode. Okay, if reset equal to 1, it is going into the functional mode. Okay, this is nothing but reset mode, and this is nothing but functional mode. Okay, so else if reset equal to 1, whatever the d value is there, that is assigned to q. Okay, end and end module. Okay, so I'm using behavioral modeling, so that's why I wrote in the always block. Okay, so this is my simple program. And if you see the test bench, if you see the test bench, so module and module name. So this is the module name, and whatever the inputs are there, I need to initialize with the reg data type, and whatever the outputs are there, I need to initialize with the y data type, and I need to instantiate the design. Okay, what is my design name? D underscore flip flop underscore asynchronous DUT. DUT is nothing but design under test. Okay, and I'm using which instantiation? Connection by name. Okay, connection by name. So whatever the variables outside the bracket, those are design inputs and outputs. Whatever the variables which are present inside the bracket, those are test bench inputs. Okay, and next I need to generate the clock. Okay, so how to generate the clock? First I need to initialize the clock to 0. Always hash by clock equal to not of clock. Clock equal to what? Not of clock. Okay, I'm generating clock with how much of time period? 10 nanoseconds. Okay, so if you are using, if you want to load this code in the EDA playground, you need to use this two commands: $dump file, d underscore flip flop underscore asynchronous dot bcd, dump vars 0 tb, this one. Okay, this you need to use. Okay, when you are using EDA playground, that is open source. No, we can use in EDA playground. And then you need to initialize the reg variables. Okay, reset underscore n equal to 0, d equal to 0. So you need to wait for 12 time units. And so I'm applying reset for 12 time units. After that, I'm releasing the reset. Okay, so here it is in reset mode. After that, it is going into the functional mode. Okay, I'm checking for the possibilities, like for integer I equal to 0, I less than 8, I equal to I plus 1. Say one possible combinations I'm checking. Okay, d equal to 1 modulus of 2 means d will toggle for 0 and 1 and 10 time units and end. Okay, and after that again trigger asynchronous reset for 7 time units, again release the reset. Final stimulus, you give d equal to 1 for 10 time units, d equal to 0 for 10 time units, and dollar finish is nothing but end the simulation, and initial begin also you end and end module. Okay, so this is the test bench. Okay, one second, this is the test bench. I want to see the circuit. Okay, save this. I want to see the circuit. So open the elaborate design. Open the elaborate design. So if you open the elaborate design, what you are getting, we'll see. See here. So this is the D flip-flop. What are the inputs? Clock, D, and this is nothing but reset underscore N. This is nothing but asynchronous reset. Directly it is given, and this is given through the bubble and clear. Okay, basically like clear and preset are nothing but asynchronous inputs. Asynchronous inputs are nothing but when they are active, irrespective of clock and input, that will force the output to either 1 or 0. Suppose if it is clear is active, irrespective of input and clock, it will force the output to 0. If preset equal to 1, irrespective of input, it will force the output to 0. Okay. So here what I given, that means reset I given to clear signal. So what? So clear is activated. So when reset equal to 0, so it is given through the bubble. So clear is activated. So when clear is activated, it is forcing the output to what? 0. So that means it is there in which mode? Reset mode. Okay. Suppose when reset equal to 1, so that means this is active low signal. So active low signal means when it is 0, it is inactive. When it is 1, it is deactive. So when it is 1, it is deactive. Deactive means what? It is acting as a functional mode. Okay. So that is the main operation of reset. Okay. And I want to simulate this. Just run the simulation. Run the simulation. Yeah. So you can see, I think you can see, okay, we'll see then the waveform only. We are not given dollar display and dollar monitor. That's why we can't see in the TCL console. We can see in the way simulation part. Okay. See here. So, yeah. So here if you see, I'll bring this towards this side. Here you see. So reset equal to 0 means it will be reset mode. Okay, reset mode. Till here, this is nothing but what? Reset mode. Okay. So when it is reset equal to 0 means the output will be what? Output will be 0 only. Okay. Output will be what? 0 only. So here when reset equal to 0, reset is active. Okay. When it is going from reset mode to functional mode, the output is not changing. When it is changing, that is reset removal is synchronous with the clock. Okay. So we given no always in the sensitivity list, always at the rate passage of clock and negate of reset. Okay. So that means this is reset removal is synchronous. Okay. So this is synchronous with the clock. So during this state, whatever the input is there, you are getting the output. Okay, during passage of clock. Okay, so here input is 0 only, you are getting 0, and here also you see input is 0. uh 1 second, where clock? Okay, input is 0, you're getting 0. During this passage you see here, during this passage the input becomes 1, the output becomes 1. Okay, it is following the output is following the input. The next state qn plus 1 is following the input. Here in during the passage of clock, this is 0. Again, it is going to 0. Okay. And next passage of clock, this is 1. It is becoming 1. Okay. During this passage of clock, see here, during this passage of clock, it is becoming what? Edge trigger. Edge trigger means what? During the edge only, the output will change. Okay. Till the next edge, the output remains same. Okay. So here 0, 0 means 0 only, and next passage of clock, it is 1, it becoming 1, and during this passage of clock, it is 0, it becoming 0. During this passage of clock, it is a 1 second, where it is passage, this is passage and one more passage. So this is a D is 1, Qn plus 1 also 1. During this passage, D is 1, Qn plus 1. 1 second, it is going to 0. Okay, it's not. What happens means here, why it is 0 means till here it is what? Functional mode. Means what? Whatever the input is there, you are getting the output. But now again the reset is applied. Okay, reset is applied. So when reset is applied, it is going from where to where? Reset mode to functional mode. Okay, it is going from, sorry, functional mode to reset mode. Okay, as I told you, no. So that means reset removal is what? Synchronous with the clock, and reset applied is asynchronous with the clock. Okay, see here, when the reset is applied, okay, 1 second, I will fit to page. When the reset is applied, what happens? Irrespective of where is this reset? This reset, see here, irrespective of clock, clock may be anything. Directly, it is resetting the output. Okay, so from this, I can give the conclusion that reset means reset removal is synchronous with the clock. Okay, reset removal is what? Synchronous with the clock. Okay, this is synchronous with the clock. Reset applied is asynchronous with the clock. Asynchronous with the clock means what? It is not depending on the clock. Irrespective of clock, it is forcing the output to 0. Okay. So basically, suppose if you take any design, okay. So basically, this type of reset we are using. Suppose if you are using synchronous reset, sometimes synchronous means what? Reset applied, reset removal, and reset applied also synchronous with the clock. Sometimes your clock will not work. You can't reset your circuit, no. So that's why reset applied is asynchronous with the clock or independent of the clock, and the reset removal is functional mode, that is synchronous with the clock. Okay. So this is very much important in the front end or DV related RTL design. Okay, you need to know about this reset and the clock and all those things. Okay. So this is about today's session. Yeah.